Okay, so some other exercise. We're done. We're done. What is this? Drawing. Oh, there is another one on conditioning. But this time we want to compute the expectation value of a continuous random variable. I think we have done exercise like this, so it's really a review. We have done things like this. So this is 7.51. So you have f of x and y is equal e to the minus y divided by y. This is if 0 is less than x, less than y, and 0 less than y, less than infinite. And otherwise, it's 0 always. And the question is, we want to compute the expectation value of x cubed. No, expectation value of x cubed under the condition y is equal to 0. Okay? We want to compute this. So what do we do? The computation is that we have to use the probability, we have to use a conditional probability. So this quantity here is the integral of x cubed times the probability of x given y of x given y dx. So what is this object here? This is in principle, it's over all R. So what is P of x given y? This is defined as the probability of x equal x, condition to the fact that y is equal to y. Right? What is this? These are two events. When we condition the two events, this is equal to P of x is equal to x and y is equal to y divided by the probability that y is equal to 1. To speak about probability is not really proper because these are, if we are dealing with density, these are probability density, they're not probability. If you want to think in terms of probability, this means you have to multiply by a small dx or dx and dy. You can multiply this by dx and this by dx and dy, and then you this by dy. Okay, so this is multiplied by dx, and this is dx dy. So this quantity is basically f of x and y. And this one is Fy of 1. And that's the quantity you want to replace here when you integrate. And then you integrate by you divide by Fy. Right? That's the quantity you want to use. Now, what are these? So this is a numerator divided by, this is a numerator divided by a denominator. The denominator is f. So let's compute the numerator. Numerator, before we do that, we should try to understand what this function is here. This function, you remember that the function is not just this. The function is this plus the domain. So this function here is non-zero only in this domain. So what is this domain in the xy plane? So first draw the domain, x and y. So y goes from 0 to infinity, and x goes from 0 to y. So there is a clear line which is x equal to y. Which one is where, what is the region where x is between 0 and y? X is between 0 and y. This is the region where x is smaller than y. This is the region where y is smaller than x. So this is the region. So we want to integrate. This is the region we are interested in. Everything else, the function is 0. Everything else is 0. So we want to integrate here. So we integrate in x. So in principle, we integrate from minus infinity to plus infinity. In practice, it's non-zero only here. So y is fixed. You fix a value of y. Okay, this is some fixed value of y, and you integrate in x. So the numerator here is the integral from 0 to y of this quantity here times x cubed. So it's x cubed times e to the minus y divided by y dx. E to the minus y divided by y, well, that's not a function of x, so this can be pulled out of the integral. And then there's an integral from 0 to y of x cubed. And that's e to the minus y divided by y times the integral of x cubed is x to the 4 divided by 4. So it's y to the 4 divided by 4. This simplifies and becomes, I will write it here, this becomes just y cubed e to the minus y divided by 4. That's the numerator. The denominator is just fy of y. Fy of y is the, in principle, is the integral over r of f of x and y dx. In practice, f is 0 except here. So that's just the integral from 0 to y of e to the minus y divided by y dx. So this is a constant, integrate in x. So that's the integral from 0 to y of dx is y. Y divided by y is 1. So this quantity becomes just e to the minus y. So when we divide the numerator divided by the denominator, the result is y cubed divided by 4. This disappears. I'm not sure that I complete the exercise here. I hope it's correct. I didn't finish the calculation. I hope it's correct. mean, did I make a mistake? Is it correct?
What is that right there? It says like something raised above negative y, like the answer. What is that?
This one?
Yeah.
What is this?
Like what is that symbol?
E to the minus y.
Oh, it's the e. Okay.
E to the minus y. That's the Fy1. Is it correct? Did you check the calculus? Yes? Okay, fine. Then another exercise. What is this? I think I ran out of it. So let's see, what is this? Oh, this one, but I have no idea. We can try to do it together. Number 6. I mean, there are a bunch of exercises from chapter 6, number 6.5, 6.6.
Professor, can I ask a question?
Yes. Yes.
Are you allowed to integrate both numerator and denominator in the, like, x cubed times the conditional density instead of integral x cubed joint density, all of which divided by marginal of y?
Oh, you mean this?
Yeah.
Yeah, sure. You write this, and then you realize that this function, this quantity here, is not a function of x. So when you integrate the x, this can be factored out. So this one, this quantity here, is the same as this quantity here. Because this quantity is not a function of x. When you compute, you integrate over x, but here x is just a dummy variable. It's not something that appears explicitly.
In the numerator, the bound is from 0 to y.
This one,
Yeah, it becomes
Here?
Yeah.
here the bound is from minus
Oh, I
infinity
understand. Sorry.
to plus infinity. And here, it is, where here. So this is the bound is from minus infinity to plus infinity. When you plug the expression of f, f is 0 everywhere except in this line. And so in the integral from minus infinity to here is 0. The integral from here to plus infinity is 0. The only part that matters is the integral from 0 to y. And that's this quantity. Okay? Okay, so I wanted to do something with the correlation and the covariance, but I didn't prepare anyone. Should we look for an exercise with the covariance?
Sure.
Anyone that you like? No?
Problem 7.38. This one here.
7.38.
38. Oh, that's the first one. This one or this one?
Oh, sure. Why don't I have it? There's a different edition.
Oh, we have to see it.
Oh, yes, it's the same. Oh, this one. Thank you. Okay, so we do a similar one. We have 7.38. So I can erase this one. random variable x and y have the joint density function given by. So it's 7.38. So x and y f of x and y equals 2 into the minus 2x divided by x, 0 less or equal x, less or equal, or less infinity, and 0 less or equal y, less or equal x, and 0 otherwise. Then you want to compute the covariance of x and y. Okay. So, how do we compute the covariance? There are two ways. The definition of the covariance is the expectation value of x minus mu x, y minus mu y, and then you can you get 4 terms in this quantity here, but 2 of them are 0 if, is it right? 2 of them are 0, yeah, no if, that's always the case. So in this case you get e, what is this? This is e of x and y minus mu x times y minus mu y times x plus mu x mu y. Right, and then this is equal to e of x and y, and then you have minus mu x mu y minus mu y mu x plus mu x mu y, so minus mu x mu y. So I'm not sure which one is better. I guess this is a slightly simpler way to do it. So we use this expression rather than the definition to compute the. So we want to compute 3 quantities. We want to compute expectation value of x and y, expectation value of x, and expectation value of y. So what is this f? F is defined here. It seems this is the. It seems that the author of the book likes this domain very much. Okay. So now x goes from 0 to plus infinity, and y goes from 0 to x. So this time. So this is y is equal to x, and then this region is where y is smaller than x. So we want to integrate here in this region. So we want to compute e of xy. So first compute e of xy. That's the integral. So we want to integrate from, which one is better? I think it's easier to integrate in y first. We integrate in y first, and then we integrate in x. So we integrate in y. The y integration in y is from 0 to x. And then you have the integration, you see, there is no dependence on y. That's why it is easier to integrate in y first. And then you have the integral. So this is from 0 to x. Dy. Oh, sorry. Doesn't make sense. That's the integral from 0 to infinity dx of the integral from 0 to x dy. And we integrate this function here. But this function does not depend on y, so we can pull out of the integral sign. But then we have to multiply this by x and y. So x and y. Okay? So the integral from 0 to x of y is y squared over 2. Y squared over 2 becomes x squared over 2 dx. So this simplifies, this simplifies. So I get the integral from 0 to infinity of v to the minus 2x times x dx.
Is there a reason why you put the dx before the actual function in the first part? Or you just like...
Oh, because the reason is for me, because if I put the dx close to the integral sign, I know that these are the extreme of x. If I put the dx very far away, then it's more complicated for me to see. This is the x, which one is? But it's only a matter of notation.
So it's the same as if you put dx at the
You
end?
put the dx where you want. It's the same. But it's only a matter of notation. Sometimes for me it's easier to put it closer because I immediately know that I integrated from 0 to infinity in x and I integrated from 0 to y in dy. But the standard notation is the standard notation would be to put both integration, and then the second one is the one that ends first, and the first one is the one that ends last. This is the standard notation. Yes?
I think you're supposed to have x squared at the end of it. Because you can cancel off the x's in the first integration. So you're left with...
Oh, right. There's this quantity here that I forgot to write down. You're right. So there is an extra x. There is an extra x. There was an x here, which was this one. Right? Thank you. So there is an x squared. Thanks. Then there is this nasty integral. I use a change of variables. This integral becomes the integral from 0 to infinity e to the minus z. So x is equal c over 2, and dx is equal to z over 2. So I have 1 over 8 dz. Z squared. Is that right? Is it correct? Okay, so 1 over 4 comes from here, and one over 2 comes from here. And then this quantity here is 2. So this is a quarter. Right? Because if I remember, I think in these days, I came across object like this. And turns out that these are equal to n factorial. Wow. Oh, that's 2 factorial. Fine. So this quantity is a quarter. So now we have to compute E of x and E of y. E of x is equal, the integral is almost the same, there is no y here. So E of x is the integral from 0 to infinity of, these are 2, e to the minus 2x, there is the x disappears, and then there is the integral from 0 to x of y, which is x squared over 2. No? E of x. There's no y here. So it's just the integral of dy, which is x. And so now this quantity here, if I multiply by 2 here and divide by 2, this is 1/2. That's 1/2, right? Don't trust me, you should check. Then I have e to the y. I mean, I think the most difficult thing of this exercise is to get them right. The previous one was much more challenging because you have to understand how to do it. Here, everybody knows how to do it, but you have to get it right. So, e of y is the integral from 0 to infinity of, now we don't have this one now. Is 2 e to the minus 2x, and then there is divided by x, and then there is the integral from 0 to x of y dy. This is the integral from 0 to infinity of 2 e to the minus 2x, and this one is x squared over 2. And this quantity here is integral from 0 to infinity, 2 e to the minus 2x. This is x. Now this is correct. Dx. If I use the same change of variables, I put a 2 here, a 2 here, and divide by. So this guy here is a quarter. Right? So the result is that this quantity here is equal e